Hello and welcome to the NASA TechRise Student Competition Project Showcase. I'm the president of the team here at Holly Springs High School, where we researched, designed, developed, and prototyped our experiment aiming at measuring infrared light efficiency as it relates to our Earth's atmosphere. Here's our team to talk more about our project.
The purpose of our experiment is to examine and test IR laser efficiency as we increase in altitude. Our hypothesis of this experiment is that as we increase in altitude, the efficiency of our laser will increase. Another thing that we're doing over here is soldering in all our components and wires into these breadboards so that we have a more strong and solid connection, as well as making our experiment more durable when it goes up in the balloon.
The power in our system flows from the payload interface board to the Metro M4 to breadboard, which connects to the individual components by two separate wires, SDA and SDO.
We utilize CAD in a lot of places. We needed it for a lot of our parts, as a lot of our electronic components are soldered, so we added 3D printed backings. We also utilize CAD to design mounts for our IR sensors. These parts that we modeled, we then 3D printed. Having this printer gave us a lot of flexibility in what we could do, as we weren't relying on external parts to come in.
Through Aerospace, we have been able to help other people come to different experiences that they wouldn't have been able to reach before. We've worked with soldering, which has helped people be able to apply themselves in different ways, which they're learning tasks that they will be able to use when they go off to college.
Our experiment works by shining an IR light onto an IR receiver, while recording the surrounding data using atmospheric sensors. Our experiment will be recording data when the remove before flight pin is pulled in order to collect data before and during the experiment. The sensors will record data during 5-second intervals.
The particulate matter sensor is a crucial part to our experiment. This device will enable us to detect any particulate, whether it's 100, 50, or 25 microns. We can then take this data post-experiment and see how it impacted the efficiency of our infrared light. This will ensure that our experiment goes well, successful, by eliminating any external factors.
Our experiment uses a combination of drilled holes and 3D printed parts to help secure all of our components in place. This allows for our parts like the M4 and the infrared emitter to be easily connected without worrying about damaging them.
The infrared sensor and emitter are key components of our experiment. This pair works by emitting infrared light from one end of the experiment box to another and being received by a 7x7 grid infrared receiver, which outputs quantitative data that is representative of the infrared light strength, which we can use to calculate efficiency with our baseline data.
The M4 board is the brains of our experiment. It allows us to communicate with the balloon and distribute power, which also allows us to run the sensors.
On top of all components previously mentioned, our flight box contains a few extra components as well. This includes our SD breakup board, which will be used to gather all data collected throughout the flight. Our temperature and pressure sensor will help to measure the atmospheric conditions outside of the box throughout our flight. And our UV sensor will help to measure the ultraviolet light inside of our box throughout the flight as well. Our GPS sensor will help for us to pinpoint our box at any point in the given flight as well. The purpose of these components is to help remove exterior factors as well as allow us to gather our own data, which we deemed as advantageous.
The final layout of our experiment box was largely influenced by the function of each component. The particulate matter sensor was placed by the opening of the box to ensure maximum airflow and therefore better readings. The infrared light sensor and its emitter are placed on opposite sides of the box and isolated away from other components to minimize interference.
Our payload examines the efficiency of an infrared laser as it ascends through the Earth's atmosphere. The box will start in the troposphere where most of the weather occurs, therefore we hope to see spikes in our humidity and pressure sensors, but there's also a UVA and UVB radiation hitting the Earth's surface, so we hope to see spikes in our UV sensor to account for those as well. The balloon will then go into the lower layer of the stratosphere where the ozone layer resides. The ozone is where oxygen we breathe is ionized to form O3 and blocks harmful UVC radiation, so we are hoping to catch a spike in our UV sensor to account for that upon reaching an altitude of 49,000 feet.
Understanding the impact an increase in altitude has on laser efficiency is important to understanding energy transfer and signal loss while in space. Especially when resources are as limited as they are in space, it's important effective techniques and procedures are put in place to reduce possibility of accidents. We can implement better grounding techniques or systems to accommodate different altitudes and its laser efficiency, hopefully making space technology even more safe and efficient than it already is.